Alrighty, so let's start. So now in firm theory, there is something, remember all these weird concepts that probably at some point you hated them. You're like, what is this homotheticity, homogeneity? Okay, but again, we're going to have them here, but because we know them, now we don't have to go over them that much in detail. But in firm theory, actually, as you can guess, some of these concepts, they mean actually more, right? So what do I mean by that? Suppose you're Arçelik and you want to figure out, okay, and suppose this is your production function and you're producing talve, right, and you're producing this coffee machine. So you want to know when you actually double your inputs, okay, or your tadım pizza. Basically, suppose you double both of your inputs, right? So you double your labor and capital. You want to figure out, suppose I doubled them, what's going to happen to my total output, right? It's going to, I don't know, how do you know? So it might double, it might increase proportionately, right? It might increase more than proportionately, or it might increase less than proportionately, right? It might not be, so how are we calling this concept? Remember, when you just multiply all these arguments with a constant t, let's say for t greater than 1, I'll tell you why I say this. So what was this? So this is basically, so we call this concept what? If this, if this t pops out as like this, f of lk, we called it homogeneous of degree 1, right? So this is the case. But this could pop out as squared. This could pop out as 1/2. We don't know, okay? So that's why in production, you see that it's going to be, and this is a very valid question, right? I want to know, I want to grow. I'm going to double, let's say I am, let's say tadım pizza. I'm going to open up another restaurant of exactly the same size, right? Same capital and such. And then I'm going to use same amount of labor. What's going to happen to my total output? Or I'm a factory, I'm going to have, I'm going to expand. I want to know how my output will change. Okay, so this is a very valid question from the point of view of the firm. So this is called, now we're going to call this returns to scale, right? Return to scale. Okay? So now let me write it down properly, okay? So, but this is going to be the same question that we ask. So we say that suppose Q equals to f of lk is your production function, and all inputs are multiplied by the same positive constant t. But of course, I mean, you don't have to increase the labor and capital at the same amounts all the time, right? So this is a special concept where you would like to literally open up an exactly, like a very similar factory at some other place, right? So you're just basically doubling your factories, let's say, okay? So multiply by the same positive constant t, okay, where t is greater than 1. I'll ask you why I need this, okay? Whenever there's a condition, there's always a reason, okay, in math, so always keep this in your mind. So basically, let's consider this. If you multiply all the inputs by the same positive constant t, and the amount, suppose this t pops out like this, lk. Basically, I double my inputs, my output doubles, right? I triple my inputs, my output triples, okay? So this is K, we call this, okay, so this is basically, this is T times Q, right? Then we say there is constant returns to scale, okay? So constant returns to scale. So we usually denote it by CRS, okay? You see that this is the definition of, you guys told me, homogeneity of degree 1, right? So apparently this constant returns to scale and homogeneous of degree 1 are actually equivalent concepts here, okay? Now, but there could be other stuff. So let's actually have this. If f of, so basically, let's say TL, TK, this pops out as, let's say, more than. So it's not T times f of LK, but it's actually more than that. More than T times f of LK. So somehow I doubled all my inputs, but now there's more space, or or somehow, or people, before there were too little people, they weren't very happy. Now there are more people, they're happier. So even the previous guys are working better. We don't know, whatever the reason is. But if this is the case, do you like this? If you were Arçelik or Tadım Pizza, would you like this? You double them and your the output actually even increases more than double. Would you like that? Yes, right? So this is basically, then we call this, guess. Then there is, what do you think it will be called? Increasing returns to scale, right? So there is actually, then we call this, there is increasing returns to scale. So I'll call it IRS. Not the Internal Revenue Service. So if in US, IRS means that, okay? So the sort of the tax office, which is, and there is this joke that, you know Al Capone? This has nothing to do with our class, but you know Al Capone? Yeah. The famous gangster, right? So the mob. So he actually, he got away from everything. So there's this joke that even Al Capone couldn't escape from IRS, okay? So he was basically, they put him in jail because of some tax fraud issues, not because of all those, murders or whatever. So he had a way to get away from all of them. But there is always this saying that, even Al Capone couldn't, get away from IRS, but this is not, this is increasing returns to scale, okay? So there is actually, it's the third one, as you can guess, is the bad case. I mean, not bad, but compared to this and this case, it's not that much desirable. So we basically said that if this is the case, LK, T times Q. So basically, it means that you double your inputs, but your output didn't double. Okay, then we call it decreasing returns to scale. Then there is decreasing returns to scale. Okay, so basically this is this. Okay, so this is actually, so know these, because most of the time we're going to get a production function, and then we'll try to figure out whether there is increasing returns to scale, whether there is decreasing returns to scale, and such. Okay. So, I told you that I was going to ask, why do you think this is the case? Why didn't I say t is greater than 0? So do you think, for instance, this would work for t, for any t greater than 0, this would work? So it should work, so if we had written this for t is greater than 0, it would have worked for the constant returns to scale, right? So because everything works proportionately. If you get half of your inputs, your output is going to be half as well, right? But here, then it's going to change the sign, right? If you take 1/2, then if you just, decrease your labor and capital, then they're going to, if there is increasing return scale, then the output is going to decrease more than half, right? So then it's going to change the sign. That's why we write t is greater than 1. But you'll see that for constant returns to scale, most of the time, I'm going to say t is greater than it, because it also works for t is greater than 0, okay? Not the other two cases, but that one. Okay, so you told me, so let's try to look at this constant returns to scale, because you'll see that from now on, in every course that you're going to take in Econ, most of the time, you'll see that to make things really easy, we assume there is constant returns to scale, okay? And it's going to be used a lot. So we need to know what actually it means. But you guys told me immediately that, hocam, this is related to homogeneity, right? So constant returns to scale means that so we say that, so when there is constant returns to scale, we said that this is kind of equivalent to saying that it's homogeneous of degree 1, right? So production function is homogeneous of degree 1, right? Then if there's constant return to scale, what else I can say? Remember, what did we say about if a function was homogeneous? Remember the other weird concept that we had? We said it's homothetic, right? Remember, so homotheticity was something, homogeneity was something stronger, right? So if there is, so a production function is homogeneous of degree 1, and then we know that this implies that production function is homothetic. Then remember, what did this homotheticity mean? What did it mean? Do you remember? So remember the Akbaba, Rahmi Koç, the example, right? So homotheticity meant what? About the indifference curves, right? So remember that when we had homothetic utility function, so what did it mean? We said that this was, for instance, Pur Akbaba's indifference curve, let's say, and this was Rahmi Koç's indifference curve, right? So you told me what? If utility function was homothetic, what was going on? Remember, it was kind of the same curve, but what did we say is that if it's homothetic, for instance, okay, let me remind you, we said MRS, if it's homothetic MRS, it only depended on the ratio, right? So we said that this MRS, so we said that depends only on y over x ratio. Remember, that's what we said. And then we said that, well, if MRS depends only y over x ratio, so along this ray through the origin, right, y over x ratio is the same. Right? So that's what we said. Exact, right? And then what if MRS depends, and which is the slope of these indifference curves? So basically, we said that MRS at this point, MRS at this point, MRS at this point, they're all the same, right? So that's what we meant by homotheticity. Along a ray through the origin, marginal rate of substitutions were all the same, right? So basically, let's call this MRS. So let's call it A, B, C. MRS at A is equivalent to MRS at B. This is also equal to MRS at C, right? Along a ray through the origin, all the marginal rate of substitutions, they were the same, right? So this is what we meant, and you guys told me, hocam, if I need to explain it to my grandma, it means that, you know, Akbaba, so these higher indifference curves, once you know Akbaba's indifference curve, you can actually know Rahmi Koç's indifference curve as well. It doesn't matter where that indifference curve is. They're just like, you know, some sort of blown up versions, radial expansions, okay, of these. This curve is a radial expansion of this curve, okay? So that's, you know, like what you can actually think of. So anything that we have said there applies to the production function as well. If you know that your production function is homothetic, then what can you say? Now I'm going to change these stuff, okay? So this is labor, this is capital, okay? I'm going to call this Q. Let's call this, okay, so this is, I don't know, this is Rahmi Koç's production, okay? And this is whose production? Let's think of this. What do they Koç? They produce what? So this is Arçelik, right? Okay, so it's basically Talve, but it's going to be. Let's think. Okay, so let's not have this. Let's have this. I'm going to call this Starbucks because apparently there are some people who like Starbucks a lot. So let's call this Starbucks, okay? And I'm going to call this the little coffee shop. Okay, yes. Let's call it köy kahvesi. Okay, so it means village, you know, a small coffee place at the village. Okay, so village coffee shop or village coffee cafe. So apparently if the production function, okay, And let's, of course, it should be the same good. So let's think of Türk kahvesi, okay? So because you might immediately tell me, and you are right, you would tell me that hocam at the köy kahvesi, you know, this coffee shop at the village, you wouldn't have those, you know, fancy gingerbread, you know, like stuff, or caramel macchiatos, right? But let's think of Türk kahvesi. But you see that it means that the small coffee shop or the little coffee shop, you can think of it as latte or whatever, right? So it means that if the production function is homothetic, it means that if I know the small coffee shop's production function, I can actually figure out Starbucks's production function, okay? So they are just, but of course in real life this is not the case. That's why homotheticity is a special case, okay? But this basically means that, okay? And also it means that if you see that when there's constant return to scale, we know that production function is homogeneous of degree 1. And we know that if it's homothetic, then production function, if it's homogeneous, production function would be homothetic. Then it would mean that marginal rate of technical substitution depends only on K over L ratio, okay? And margin rate of technical substitution at A, margin rate of technical substitution at B, margin rate of technical substitution at C, they're all the same, right? So if someone asks you what is homotheticity in a production concept, you said that, oh, along a ray through the origin, if you look at the slopes of these isocons, which are margin rate of technical substitutions, they are all equal to each other because they only depend on K over L ratio, okay? So that's what you guys would say, okay? So this is basically homothetic, what we mean by homotheticity. But now let's actually see this. So, okay, fine. So I figured that the constant returns to scale, then it should be production function should be homothetic. But do you think, for instance, let me put it this way. Do you think, for instance, I have an increasing returns to scale, and again, my function is homothetic? Do you think it's possible? Or let me put it this way, so you can get it easily. So in order to be homothetic, does the production function have constant returns to scale?
Yes.
So look at these signs. This has two sides, right? So it goes both ways. But this goes, I did this on purpose. There's not this part, right? Because we know that if it's homogeneous, it's homothetic. But if it's homothetic, it doesn't necessarily be homogeneous, okay? So you can see that you can have increasing returns to scale, and the function could be homothetic. So I'll give you an example on that. So just keep this in your mind. So basically, the other side is not correct. So let's actually have a look at that. So let me ask the question, write down the question so that you would have it nicely in your notes. It's obvious from there, but so let's say in order to be homothetic, do we need constant returns to scale? And the answer is no. Because you see this goes in one way. It doesn't go the other way around. So there could be some homothetic functions which are not homogeneous, right? Which basically where we don't have constant returns to scale. Now, for instance, consider this example. Consider, so this is basically, you're trying to come up with a counter example, okay? So basically, it is, you're trying to come up with an example which doesn't satisfy something which is homothetic, but doesn't show constant returns to scale. Then you would say that, oh, in order for homothetic, it doesn't have to exhibit constant returns to scale. Okay, so that's called a counter example. Okay, so this is going to be f of, suppose you have a function like this, f of lk. I define the function in such a way that, so this gamma is greater than 1. Okay, so this is the case. This gamma is greater than 1, where f of lk is homogeneous of degree 1. Okay, or you can say there is constant returns to scale, okay? Has constant returns to scale, whichever one you would like to use, okay? So these are equivalent. So this is the case, fine. Now, in order to show whether it has, so this is, remember, how did we define homotheticity? One of the definitions that I have written, okay, I told you that it's actually a positive monotone transformation of homogeneous function, which is by design like that, okay? So it is actually homothetic. So we know this guy is homothetic, okay? So this is homothetic since it is a positive monotone transformation of a homogeneous function, okay? So we know that it's homothetic by definition, so don't worry about it. All I want you to show is that this shows what? So let's see, in order to see the returns to scale, what should I do? Remember how were we, so I erased it, but in order to, you know, like figure out whether it has constant return scale, increasing return scale, remember what do? You multiply, right, by a constant, positive constant t. So let's do this. So I need to look at this. T times L, t times k, right? So for any t greater than 0, or let's put it greater than 1, because that was the, okay, so let me check this. Okay, so let's do this. TL, tk. Okay, so I know, let me write this. Apparently, if this is the function, then I write this. So basically f of, so it is like this, right? T times L and t times k, L, t times k, okay? To the power gamma. Okay, so we know, what do we know about this guy? What did I say? I said that this is homogeneous of degree 1, right? So then if it's homogeneous of degree 1, this is equal to what? T times, right, f of Lk. Okay, so let me write this. So this is by t times f of Lk to the power gamma. Okay, so this is t to the power gamma f of Lk, right? So this is basically, so that's what we say, right? So, and this guy to the power gamma. Okay, what is this guy? Does it look familiar? Right, so this is this cap f, right? So this is basically, so this is equal to, so you see that this is f of Lk. So you see when I multiply everything by t, all the arguments, all these inputs by t, by a constant t, this t pops out as t to the power gamma and this guy, right? So the old function. So then, what do we have here? Increasing return scale, decreasing return scale, or constant return scale? Remember, I said this. You could told me that, Hocam, it depends on this guy. If this is greater than 1, then we would have increasing return scale. If I had said that this is less than 1, you would tell me decreasing returns to scale. If I had picked this guy as 1, then it would be this homogeneous function, and we know it's by definition homothetic, okay? So you see here I have IRS, but this is a homothetic function. So it doesn't have to be, you know, like you can have a homothetic function, but it could be showing some other returns to scale phenomena other than constant returns to scale, okay? So just, I think this is a nice example to show, you know, like whether, so I'm going to give you a function. I ask you, please show me whether this shows increasing, decreasing, or constant returns to scale. What you would do is that you're going to multiply all these arguments and try to figure out this f of TL tk is equivalent to t times this guy. But you know, what is the exponent, for instance, here, okay? Is it doubling or is it like t times that guy, or it's more than, you know, like t times that guy, okay? So this is basically what we will do. Now, remember also in consumer theory, we introduced this, again, weird concept called elasticity of substitution. Remember, CES was constant elasticity of substitution utility function. Here, we're going to have also CES production function. So it makes actually more sense here, I would say. That's what I told you, I think, in consumer theory, if I remember, okay? So the elasticity of substitution is going to be a very similar concept that we're going to be dealing with. So now it's going to be, so basically it means, just always keep in your mind that the elasticity of substitution, whether it's in the context of consumer theory or firm theory, okay, it is actually related to the curvature of these curves, okay? And basically it means how easy it is for you to substitute capital or to substitute labor for capital, okay? So if things are really easy, then we say there is the elasticity of substitution is high. If things are hard, we actually say that the elasticity of substitution is low, okay? So basically, so what's happening is the following. I'll give you the definition. So basically, elasticity of substitution, so this is called elasticity of substitution. So in the firm theory, it's defined like this, okay? So this is basically, so that's what we said, percentage change in K over L ratio, percentage change in marginal rate of technical substitution. So basically, it's actually easier to interpret this from the other way around. It means that if I change K over, so let's call this KA, LA. So if I change K over L mix, okay? How would, so I know that I have a marginal rate of technical substitution here. So if I change my K over L mix, you see a lot, so KB, LB, let's call. So I'm changing the ratio of K to L. How does my marginal rate of technical substitution, you know, like basically change, okay? So does it respond a lot? So is it, so that's the whole idea. Is it easy for you to substitute or it's hard for you to substitute? For instance, if I had, just as we had it in the consumer theory, suppose I have these indifference curves, right? Remember, I have these isocons like this. Then what's happening? When I change K over L mix, how does margin rate of technical substitution change? It doesn't change at all, right? So it's the same. So in this case, we're going to call these capital and labor, or we call these goods, remember, in the consumer theory, perfect substitutes, right? So you see they're easily substitutable. They're perfect substitutes. So the elasticity of substitution would be high, okay? Or think of it like this case. Now, if as soon as I change the input mix from here to here, right? Then here, the marginal rate of technical substitution is actually infinity. And here it's 0. It changes a lot, right? So basically, can you easily substitute them? No, because they're perfect complements. And remember, like Cobb-Douglas was a case in between these guys, right? So, and CES was also like a case which was covering all these, right? So basically, so here in the Cobb-Douglas case, you can substitute them to some extent. They're not perfect complements. They're not perfect substitutes. There is some substitutability, okay? But not perfect, okay? So this was the Cobb-Douglas case, okay? So this is what we mean by elasticity of substitution. Think of it like that. How easy for me to substitute one good for the other one, okay? So this is, and there are many ways of writing this guy. So one is del ln K over L, because you see it's the percentage changes, okay? So you can write it as the derivatives of the logs if you want, okay? So this is ln MRTS, or if you want, you can just write percentage changes like this. So they're all equivalent to each other. So this is going to be basically del K over L, K over L, del MRTS, del MRTS, okay? And then you can have it del K over L over del MRTS. You would see different ways of expressing this, okay? So this is basically the elasticity of substitution. And what do I know about this marginal rate of technical substitution? If you want, you can also write, instead of this guy, you can actually write this guy like this, K over L, del. What is marginal rate of technical substitution equal to? What did we say? It's equal to the ratio of the marginal products, right? So you can, in some cases, you would see that it's expressed like this, MPL, MPK, MPL, MPK, right? And K over L. So you can also interpret it like this. Oh, I'm changing. When I change this capital to labor ratio, apparently the ratio of the marginal productivities change as well, right? So if the ratio of the marginal productivities change a lot, I might not want that, right? Or if they don't change at all, I can easily change my K over L ratio. I can easily use one input for the other, okay? So this is basically, so the concept of elasticity of substitution is basically that. And as I told you that in this case, for instance, in this perfect substitutes case, this is going to be basically, so if you look at here, so this is the perfect substitutes case. So the elasticity of substitution is going to be very high here. And so you say it's high, is high, okay? And for the perfect complements case is going to be low, okay? And then for instance, Cobb-Douglas and all the other cases would be somewhere in between, okay? Now, as you can guess, in production, we're going to have our good old extreme cases, perfect substitutes, perfect complements, and Cobb-Douglas again, okay? Now, let me write this. So this is basically the case, right? So this is, let's put it. Now, if you missed our functional forms, let's come back to this. So we would have perfect substitutes, okay? We would have perfect complements, okay? And we would have, we're going to have Cobb-Douglas. We would have the Cobb-Douglas form, okay? Now remember, perfect substitutes, apparently it's going to be a case where capital and labor are perfectly substitutable for each other. So let's call this Q0, Q1, okay? And this is, let's say Q2, okay? So what could be the case? For instance, we were talking about the coffee machine, right? Coffee machine, Talve, and your mom, right? Making the Turkish coffee. So they're like perfect substitutes, right? You can easily substitute your mom for a coffee machine, right? So, or a coffee machine for your mom, right? So it's actually the case for making Turkish coffee, okay? Or you can think of, remember the vending machine there. If I put one person to sell all those Coke, do you think it's easily substitutable? You can, but remember these are extreme cases, so it's very hard to find examples. But you can think of a vending machine and a person selling the product. You can think of the coffee machine and your mom, right? So it's making Turkish coffee. We know that they are perfect substitutes. And in this case, remember, how were we writing the utility function or the production function here? In the perfect substitutes case, how can I write down the like the production function or the utility function that would give perfect substitutes? Linear. Right, so it was linear. So we were saying alpha, right? Alpha times L, beta times K, right? So it's very, very similar as you see in the utility. Before we were writing U of xy, alpha times x, beta times y. Now we do it in the production theory like this, okay? So what is the marginal rate of technical substitution here, as you guys know? What is it? Remember, this was the slope of the isoquant. What is the slope here? Minus marginal rate of technical substitution, right? So the slope here it's actually the absolute value of the slope. So the slope here, as you said, hocam, it's minus alpha over beta. So the marginal rate of technical substitution is alpha over beta, okay? What is elasticity of substitution here? So if I look, so let me try to figure this out. When I change K over L, this guy doesn't change at all. It is, so this is 0, and there is some number here, some number divided by 0. What is it? Infinity, right? So apparently elasticity of substitution, let's say, goes to infinity here. So you see that obviously these are perfectly substitutable goods, okay? So now what about perfect complement? So let's try to see in this case. So this is K over L, and the perfect complements I was writing like this, right? Q0, Q1, whatever. So, and there could be some sort of, you know. So these were inputs or goods in the consumer theory that you need to use in some fixed proportions, right? So these were called Leontief and such. Remember? So how were we writing this production function? How were we writing the utility function in the perfect complements? It was minimum, right? So, okay, let me tell you. Suppose I would like to have, so let's say perfect complements. Suppose one airplane goes with 2 pilots, right? So if I have an extra pilot, do you think it's going to make any difference? No, I have another pilot. It's not going to be, but you need two, right? Or for instance, you know, like my car and me, right? So all you need is one driver, right? So if you have an extra driver, it's not going to change anything, okay? So you can think of these inputs like that. But it's actually, so you see that, but how are we writing this? So how are we writing the production function? So let's put it like this, Q f of Lk. Okay, f of Lk. Remember, we were using minimums. Suppose I would like to use a beta units of labor with, I have to use with alpha units of capital. Okay, suppose this is the case. If I use beta units of, so let's put it, 2 units, 2 pilots, 1 airplane, 1 plane. Okay, so how shall I write this? We were writing minimum. It was, remember, you were just changing the place. So it's actually alpha L, beta K, right? So this is basically how we were writing the case for the perfect complements. What is marginal rate of technical substitution here? What is the slope of the isoquant? You said, is it 0? You said that it's hocam. It depends. It's not defined here, right? And what is it here? If you think of it, you know, just conceptually, what is the slope here? It's infinity, right? And the slope here is, it's flat, 0. So you see, and so we can actually say is not defined at, you know, this point, let's say point A. Yeah, at King's, let's put it, okay, at King's. In the other places, we know, so for instance, if you're thinking of the elasticity of substitution, suppose I change my input mix from here to here. How would my marginal rate of technical substitution change? Suppose I change this, how would this guy change? A lot or little? A lot, right? From infinity, it becomes to 0. So it's just some numbers divided by infinity. Think of it like that. Then elasticity of substitution should be 0, right? So basically, of course, this is, you see that, so the elasticity of substitution it goes to 0. Basically, they're not substitutable. It's very low, okay, possible. And as I said that in the Cobb-Douglas case, it is some case in between, L, K. So this is the perfect substitutes. This is the perfect complements. So Cobb-Douglas is going to be not as flat as this guy, not as kinked as that guy, but somewhere in between. Okay, now I erase these guys. So you see that? So this is Q0, let's put it Q1, let's put it Q2, okay? So how are we writing for the Cobb-Douglas? The utility function, and here it's going to be the production function. Nasıl yazıyorduk? So we can call it, we can have the A times blah blah, but so this is basically, so this is, let me see, yeah, let's put this. A times L to the power alpha, K to the power beta, okay? And we were saying A is positive, L is positive, alpha is positive, and beta is positive, okay? So this is basically the case. So I'll give you this small task, and here, elasticity of substitution. Guess what this is? So try finding this. It should be 1. And a tiny task, so we'll stop here, but for you, is that, do you think we have, in this case, IRS, constant returns to scale, increasing returns to scale, or decreasing returns to scale? Which one? And similarly here, which one? Similarly here, which one? Okay? So try to figure those out. Now you know how to. For instance, in the first case, if I multiply all these inputs by t, the output is going to t times that, right? So there is constant return scale here. What about here? I multiply this guy t, this guy t. This t comes up t times minimum alpha L beta k. Because it doesn't matter in the minimum, right? So suppose this, I have this minimum of 2 and 5. Minimum of 2 and 5 is 2. So I multiply these guys by 2. So this is 4, this is 10. The minimum is still going to be, you know, like the minimum, right? So the minimum is going to be 2 times the previous minimum, basically, right? You can always write it like this, okay? So there is constant return to scale here as well. What about Cobb-Douglas? Okay, so this is kind of your task. Do it for the exam, okay? And we'll go over it also in the reviews. What about this? So just try to show that it's 1, okay? And then also try to show whether there is CRS, IRS, or decreasing returns to scale here, okay?